Good afternoon, AP Stats kids. It's Thursday, April 9th. I'm Mr. Murphy, and I'm talking to you from Bangor, Maine. I hope everyone is at home safe and healthy and able to kind of keep up with their work, and let's all stay positive and let's hope we can beat this virus. Hopefully you can't hear the wind, but we're going to get what they call a nor'easter. We're going to get a good 8 to 18 inches of snow tonight. And it's a heavy, wet snow, so we could lose power. But I think I'm going to be fine this afternoon. The wind's picking up a little bit. No snow yet, but we have a winter weather advisory from now until tomorrow night at 6, so maybe good timing. You'll be with my good friend Luke tomorrow. He's going to do type 1, type 2 errors and power. Those are concepts that are perhaps a little bit more difficult for kids, and Luke will do a great job at that. So hopefully you can tune in tomorrow to hear Luke. I may be out shoveling snow tomorrow, so. Yesterday he did confidence intervals with means, probably both 1 and 2 samples. And today I'm going to do hypothesis testing with means, both 1 and 2 samples. And hopefully at this point you're really starting to see that, you know, how we build confidence intervals is pretty consistent, no matter whether we're dealing with means or proportions or inference for regression and slopes. Hypothesis testing, probably the same thing. You're starting to see over and over again, you know, they have certain things that they're looking for, and they always start out with the name of the test and those things. So we hope that this has been good review. Again, the first 2 units that we did, chi-squared and inference for regression, those are not on this year's modified AP Stats exam. So if you want to forget about those for this year's exam, that would be okay. We decided to continue on with inference, not knowing exactly where you were perhaps in your classroom with your teachers. We weren't sure exactly, you know, how much your teachers had covered with you. And so while we were doing inference, we decided, let's just finish inference. Let's do a good job with inference and, you know, proportions and means, 1 and 2 samples, confidence intervals, hypothesis test, power, all that. Starting next Monday, we will kind of go back to the beginning of the year, you know, chapter 1, exploratory data analysis, graph types, those types of things, mean, median, mode. And the schedule for the rest of the year is published, and that's on AP Central, and I'll show you that in one of my slides. So let's go ahead and look at last night's homework, and we'll dive into today's session. So again, I don't know why I like this picture so much, but I do. It's just a cool little graph, right? Again, my name is Brendan Murphy. I teach at John Baptist Memorial High School in Bangor, Maine. And the principal sent out a kind of a funny email today and said, you know, teachers, probably tomorrow is going to be a snow day, but I guess we've had a snow day for the last month. But we're going to get a pretty good storm up here. We're going to get some good snow. And hopefully you've been able to watch my good friend Luke. Luke and I have worked with each other literally for years. We're pretty good friends, and he's awesome. And I actually like to listen to him some afternoons when I don't have much going on. He's a great teacher, so I enjoyed listening in with him. So here's last night's homework. Hopefully you had a chance to look at it. I'm just going to go to my overhead projector here. We'll take a look at it. So a soda manufacturer claims that its Cherry Fizz soda has more carbonation than a competitor's Cherry Eclipse soda. Sort of feels like I'm going to compare 2 different types of sodas here. Bottles of both types of soda are opened, covered with a balloon, and then shaken. Science experiment, maybe, I don't know. The diameter of each balloon is then measured. The mean balloon diameters are 2.3 inches for the Cherry Fizz soda and 2.1 inches for the Cherry Eclipse soda. So they're similar, I guess, in diameter, but is that difference enough to say that there is a difference? And of course, I can't look at those numbers any more than you can look at them. I'd have to run some sort of a test or a confidence interval. A 90% confidence interval to estimate the difference in mean diameters in inches is negative 0.8 to 1.2. So there's my interval. I typically want, well, I almost always want high confidence. Of course, as I get higher confidence, the interval tends to get bigger. And so it's sort of a trade-off, right? Which of the following claims is supported by the interval? So if you've listened to any of my sessions on inference, I typically have, like 4 questions that I like to ask my students to kind of get into the problem and maybe name the test. So question 1 is, does this feel like a confidence interval or a hypothesis test? And It says 95% confidence interval, excuse me, 90% confidence interval. So pretty convinced it's a confidence interval. Some teachers have rephrased that to me and said, you know, Brendan, as opposed to saying hypothesis test or confidence interval, are we creating some numbers in an interval, or do we want a yes or no decision? And I really like that. So I think I'm going to maybe improve that next year when I teach it with my kids. So it feels like a confidence interval. Do I have one or two samples? Well, it feels like I have the two different types of sodas, and so it feels like two samples. Then I say something like, are we dealing with proportions or means or averages? And it feels like we're dealing with means, right? It says the mean diameter is 2.3 and the mean diameter is 2.1. And then I say something like, if we were going to go read do we go read a T table or a Z table or something to that effect? And by naming the test, it really helps my kids kind of get into the problem, set the stage, hopefully answer it correctly, and going and finding the right test on the calculator. There's one button, and we'll go there later today, and there's a whole bunch of tests there, and it is confusing. So those 4 questions have helped my students get into the problem, write the name of the test. That's the first thing I do, and you'll see me do that a couple times today. And then when I go to the calculator, it does help me find the right test. And we'll talk about when we do a hypothesis testing, if you do the name of the test, you don't need the formula. So that's a good thing. So I need to look at that interval, negative 0.8 to 1.2. Which of the following is supported? Because 2.3 inches is larger than 2.1 inches, the manufacturer is correct, and Cherry Fizz has more carbonation. I don't know if I can say that. We've taken a small sample here, and 2.3 is definitely bigger than 2.1, but I don't know if I can make some claim about these two different types of soda. Because the interval has more positive values than negative values, Cherry Fizz has more carbonation. I don't think that's a true statement either. It doesn't really matter how much is positive and how much is negative. Hopefully you're already zooming in and saying, we're looking for 0. We're looking for 0. Is 0 anywhere in that interval? So I don't think A and B makes sense. Because 2.3 and 2.1 are very similar, there is no difference in the mean carbonation levels. The first half is a true statement, but I don't think I can make the leap to the second half. So right now, I don't like any A, B, and C. The interval cannot be interpreted because negative measurements are not possible. That doesn't feel good either. It just depends upon how I'm subtracting. And so let's hope E makes sense, because A, B, C, D does make sense. E, because the interval contains 0, it is possible that there is no difference in the mean carbonation levels. And yeah, that's a great sort of one-sentence analysis of interpreting two-sample confidence interval. We're looking for 0 anywhere in that interval, and it doesn't have to be right in the middle of this interval. It literally can be anywhere in the interval. So I get answer E. I think that's correct, and hopefully Luke did a good job of that yesterday. So I'm going to go back to my PowerPoint here, and we'll get started with today. So there's the homework problem again. We just went through that. If you've been with me before, you've seen these first 2 web addresses. I added the third one down here, and this currently has online AP Central the schedule for the rest of our 3.5 weeks that Luke and I are going to do. So we've gotten emails from both teachers and students, which is really cool. People have seen our name and somehow looked up our emails at our school websites or something. You can go and see what we have planned literally for the next 3.5 weeks. We realize that you're busy and lots of work going on, and I think AB Calculus goes at the same time as us. And so if you're taking more than one AP course, you may want to sit on them both. So you can go there and see exactly what we're going to be discussing literally for the rest of our time together until May 1st. So if you go to this bottom website, you'll have the schedule kind of at the top of all the different classes. Keep scrolling down until you get to math and science. You'll have all the math and science AP courses. Click on AP Stats, expand all, and then you'll see the schedule that we've given to the College Board. So tomorrow Luke is doing Type 1, Type 2 Power. And then I think the last week when we're kind of really zooming in and laser focusing on helping you get ready for this year's modified AP Stats exam, one of the days, and I can't remember if he's doing it or I'm doing it, is, name that test. Here's a problem. What type of test do we want to do? So that's good. That schedule is up. Please share that with your friends and colleagues and your teachers and whatnot. And hopefully that can help you just prepare better for this year's AP Stats exam. So, okay, so I'm going to be talking about hypothesis tests with means, both 1 and 2 samples. And so here's kind of the first formula that we need with a 1 sample t-test, I guess. And anytime we're dealing with means, we need to be concerned about degrees of freedom. And I'll tackle that one. There's sort of a little nuance there about degrees of freedom when we get to 2 samples. And I copied this right from the College Board CED, Course and Exam Description booklet. That's something that we as teachers sort of look at. You will not find this formula exactly on the AP Stats formula sheet. But typically, the difficult thing here is, this standard error here, this standard deviation based upon sample size. That's sort of what my kids struggle with the most. So hopefully you're feeling more comfortable with all of these formulas. There's no reason to memorize them. The calculator will do all of these. And of course, this year's test is going to be open book, open note, and maybe you have these highlighted in your book or something. So I'll leave that up to you. So that's sort of a 1 sample hypothesis test with means. This formula is a little bit more intimidating. This is for 2 samples. And again, I just copied this right from this College Board CED. The note down here, though, t-distribution with degrees of freedoms that can be found using technology. So I'll tackle that one. I'm not sure if Luke did it yesterday, but what do we do in 2 samples if I have 2 different sample size? How do we figure out this degrees of freedom and whatnot? So that one's on my list of things to do this afternoon, and we'll be good there. Let's not worry about this formula. It's not part of the curriculum. I'll come back to it really quick when we do a problem. So here's kind of the 4 questions, again, that I always ask my students anytime we're doing an inference. So at this point of the year, if I had been in school with them the last month, they would honestly probably be sick of me and sick of these 4 questions. But, does this problem feel like a confidence interval or a hypothesis test? We have 1 or 2 samples. We're dealing with proportions or means. The other day, I like to, like say, which highway are we on? Are we on the proportions or mean highway? Once we get on that highway, we don't get off it on that problem. And do we need to read a Z table or a T table? Again, your teachers may have shown you how to do it on the calculator, which is perfectly fine. I'm a little old school. I still like tables, and I like to show my students both. But if you're not comfortable with a T table or a Z table, don't worry about it. Your calculator can get all these values. And if the students can answer all these questions correctly, I think it helps them, 1, name the test, which is super important on a free response, and then get into the problem and hopefully solve it correctly and find the right test on the calculator. So those 4 are really designed to help my kids sort of quickly get into the problem. So I'm going to look at, I think, at least one multiple choice and a couple of free response today. So let me give you a minute to read this one. This was a multiple choice from the 2012 exam. And I think sort of the goal of this problem was can you identify what type of test are we going to do? What's the name of this test, I guess. So let me give you 30 seconds or so to read this. I'm going to go over to my document camera and we'll walk through it together. So hopefully you can still see that. Okay, so a manufacturer claims its brand A battery lasts longer than its competitor's brand B battery. Okay, we want to compare 2 different batteries and see which one lasts longer. So pretty real world problem, right? 9 batteries of each brand are tested independently. Boy, that's kind of an important word here. I might underline that if I was a student. And the hours of battery life are shown in the table below. I'm looking for the word random, and I don't see that, but hopefully it's coming later or something. So I picked 9 batteries from brand A, and seen how long the batteries last or something like that, and done the same for B. So it feels sort of like I have 2 different samples here, or excuse me, I have 2 samples here, but I have the same number of tests, I guess, or same number of data points for each. And so anytime I see that, I just make a little note to myself, could this be a matched pairs? Now, it's not that simple, and again, I'm going to tackle that a little bit later, but it feels like I have two things I'm comparing, brand A and B. Could this be a matched pairs problem? And I'll try and talk about the difference between what's the difference between a matched pairs with means and a two-sample t-test. Provided that the assumptions for inference are met. Okay, so that's good. So I think I'm covered here with my randomness and sample size and all those things. Which of the following tests should be conducted to determine if brand A batteries do in fact last longer than brand B batteries? Okay, so here's my 4 questions again. Does this feel like a confidence interval or hypothesis test? Well, it sort of feels like a test, right? That's my little keyword there. Do I have 1 or 2 samples? I have 2 samples, but again, I need to be kind of thinking about this matched pairs test here in the back of my mind. Are we dealing with means or proportions? No, I think we're dealing with means, right? Average hours. And am I going to read a Z table or a T table? So when I answered those 4 questions, I came up with a 2-sample. Boy, my writing is atrocious, isn't it? Hypothesis test with means. Okay, so that was the name of the test. And I didn't need to do this, but I felt it was going to maybe help me. So I just came up with what my null and alternative hypothesis. So mu of A equals mu of B. And so that would be the population of both those brands' batteries and how long did they last. And I think up here it says, does A last longer than B? And so that gave me a little clue for my alternative. And so I said mu of A is greater than mu of B. Of course, on a multiple choice, perhaps you don't need to do this. If it helps you, great. If it doesn't, that's okay. It's not needed in the problem. So I went up here and it sort of felt like I could get rid of D and E. Those are talking about Z tests. And, usually when I hear Z, I think proportions, and T, I think means. A 2-sided, 2-sample t-test, well, it is one-sided, so I was able to sort of get rid of that one too. So the question is it A or is it B? And again, when I have the same number of, my sample size is the same, I at least think about matched pairs. The more important decision about whether it's a matched pairs or I guess what we're calling a paired t-test versus a 2-sample t-test are those independent of each other or are they not independent of each other? So it feels like brand A and brand B are independent. They're not related to each other. Brand B is not going to work longer or less than brand A. So because those were independent, that led me to a answer B here. So answer B, I'm pretty sure, is the correct answer. It is a one-sided, mu of A is greater than mu of B, 2-sample t-test. And so I'm going to do I think my next problem is going to be a matched pairs, and hopefully you can kind of see the difference here. So brand A and brand B are independent of each other. The batteries aren't in cahoots. A is not working longer than B. They're totally separate. And that led me to the 2-sample t-test. So hopefully that helps. And so I found a free response from 2006, and hopefully these free response and multiple choice that I'm doing and we're giving you for homework are helpful. Again, this year's modified AP Stats exam is all free response questions. So we really want you to get in the habit of reading them and analyzing them and hopefully coming up with some really good, solid, what I call free response answers. So you haven't seen this one before, so let me just give you a minute to read that one. A lot of data here, and I hopefully have typed it into my calculator already, so I'll try and save some time. But see if you can perhaps tell if this is a 2-sample t-test or a matched pairs t-test. And the key decision that I need to make are, is in this case the before and after independent of each other, or are they not independent of each other? So I'll give you a minute or so to read this, and then we'll dive in and I'll work through my solution. Okay. The developers of a training program designed to improve manual dexterity claim that people who complete the 6-week training program will increase their manual dexterity. Okay, just setting the stage. That's what I say to the, we want to get you into the problem. A random, that's always a good word, sample of 12 people enrolled in the training program was selected. Random sample of 12 people enrolled in the training program was selected. Okay, I like random. That feels a little low to me. I always am more comfortable with a larger sample size, but 12, it is what it is, and I have to do my analysis that way, and we'll have to address that when I'm dealing with conditions or something. So it's like I like the random, the 12. I wish that were 24 or 120 or something. A measure of each person's dexterity on a scale from 1 lowest to 9 highest was recorded just before the start and just after the completion of the 6-week program. So it sort of looks like that's what all of these numbers are. So for person A, we measured their dexterity. Again, I don't really know what a 6.7 manual dexterity means, but higher number is better. You're more flexible. And at the end of the program, or 6 weeks later, for person A, their dexterity had gone up. Okay, doesn't mean anything. One person goes up, the next one could go down. And I think that's what you're seeing here for those 12 people. So we have the before. This is when they were randomly selected at the beginning. We somehow measured their manual dexterity, and they went through some 6-week program that was designed to improve their manual dexterity, and then we took a measurement here afterwards. So again, anytime when I have the same number, I at least think, could this be a match pairs test? Okay, so same 4 questions. This feel like a confidence? Excuse me, I don't know what I'm supposed to do yet, sorry. Can one conclude that the mean manual dexterity for people who have completed the 6-week training program has significantly increased? Support your conclusion with appropriate statistical evidence. So statistically significantly increased. I'm leaning towards a hypothesis test here, I think. There's no confidence level here, so I think it's some sort of a hypothesis test here. So, that's my first question. Does it feel like a confidence interval hypothesis test? I'm going to go with the hypothesis test here. Do I have 1 or 2 samples? It clearly looks like I have a bunch of data here and a bunch of data here before and after. So it's very easy to say 2 samples here. So for now, let's say I have 2 different, sets of data here, and I somehow need to compare them or something. Are we dealing with means or proportions? These look like averages or means, not proportions. So I'm going to go with the means. And am I going to read a Z table or a T table? So I think I'm going to go with the T table with means. So here's the decision. Is this a match pairs test, or is this a 2-sample T test? If these 2 sets of data are independent, like we saw in the last multiple choice, then it's a 2-sample T test. If they're not independent of each other, they're related to each other in layman's terms, then it's what we call match pairs. So anytime the sample sizes, for lack of a better term, are the same, I at least think of match pairs. If the 2 sample sizes are different, it can't be match pairs, at least in our course here. So anytime they're the same, think of match pairs. I think I'm going to go with match pairs here because it feels like the before and after aren't independent. If I scored well here, I'm probably going to score reasonably well here. So the before and after do not feel independent to me at all. It feels like I have some manual dexterity, and they measure me, and then I go through a training and they measure me again, and those feel like they're related. So I wanted to call this a match pairs T-test with means. Lots of other ways to phrase that. That's just sort of my way of doing it. That's based upon my 4 questions. And again, if my 2 sample sizes, for lack of a better term, are the same, I at least think match pairs. The bigger decision is, are they independent or not independent? So my null hypothesis is mu of the difference. So that's that little d is 0. There's no difference. The program didn't work. No difference between 4 and after. Going back up here, has the 6-week training program has significantly increased? Okay, well then the mu of difference is greater than 0, so people have become more their dexterity has improved over that 6 weeks. Always, always, always identify your parameters. So null and alternative, name of test, that's sort of how I always do all of these problems. Mu of D is the mean difference before and after, and the dexterity scores for the population of people enrolled in this program. Again, I don't know how many people are enrolled in this program, but null and alternative, always identify your parameters. Naming the test is helpful. That allows me not to come up with what I call the generic formula. So we're heading down the right path. I want to check my conditions and assumptions. So it did tell me the 12 people are a random sample of people in the program, so that's good. I did actually subtract my after and before. I'll show you that in the calculator in a second. So when I'm doing matched pairs, what I'm really doing is usually taking the difference of my two different groups of data. And so the first person went up 1.1, the second person went up 0.5, this person, nothing happened. These people, the program didn't work at all. They actually went backwards. And so I came up with those, and I'll show you those in the calculator in just a second. Well, I think I said earlier I was a little bit worried about that sample size of 12, right? I wanted that to be bigger. And you know, you may have the number 30 in your brains with means. Well, usually when we test matched pairs, you know, you got to type these numbers into your calculator, and 12 times 2 is 24. And so if we had 30, it would be 30 times 2 and 16. It just takes too long. So for these problems, we understand that, you know, you're racing the clock and trying to do them. And so, you know, it's not atypical that you might only have 8, 10, 12, again, times 2. And so I decided to do a quick dot plot of the differences. And so I put a little dot plot together here. And I'm looking for huge skewness, obvious skewness, or any outliers. And I didn't see that, and so I just made a little note over here. There's no obvious skewness or outliers, so we'll assume approximately normal. And that's the best I can do with 12 data points. Again, I would like that to be way higher, but if we had 20 or 30 in 2 columns, boy, it would take you forever to type that in. So this is a really old problem. We really weren't worried way back then about population and the 10% condition, but moving forward, starting in 2019, we do think it's important. So is the population greater than 10 times the sample size? Is the population greater than 10 times 12? Is the population greater than 120? And I don't know that for a fact, but I would probably just put a few words over here that it's reasonable to assume that the population of these people, you know, is greater than 120. Again, I have absolutely no idea. But we want you to at least think about that. And so this one here is an assumption. I can't check that. I don't know that for a fact. So I think we're good with our conditions. Again, here's my general or generic formula. I do not need that. You do not need that anywhere on your paper. If you've named the test correctly somewhere on your paper, and my kids always find that easier. So I'm going to just go back to the calculator and show you where I got all of those numbers. We'll run the test. So I think that in my list 1 and list 2, yep, I was efficient earlier today. I listed those 12 values. This is the before and this is the after. And I'm interested in the difference. So I had to subtract those two. And so for list 3, I said, you know, list 2 minus list 1. And now list 3, I'm almost going to run this test like it's a one sample t-test. I have my two sets of data that I've combined, I've subtracted, I have the difference. And now I'm going to, at least from a mathematical point of view, I'm going to run it like a one sample t-test. So I have all those numbers typed in. That's good. I'm going to go run a test. So again, there's no test here for matched pairs. That's what I wrote on the first page of my answer. But I'm going to handle this like a one sample t-test. And so I think I can run my data. Okay, sorry about that. I have the data in a list, so I'm going to run data as opposed to stats. My null is equal to 0. My difference, there's no difference between my two groups. My data is in list 3. I think my alternative was greater than, so I need to change that one. And I'm going to get some numbers here. So these are the key numbers that I need to write on my paper. So I'm going to go back to my paper here. So this t statistic, this p-value, those are important. Again, if you've named the test correctly, that's really all we're looking for math and mechanics. Now I have a little bit more. X bar of the difference was 0.375. The calculator gave me that. SD was 0.367. The calculator gave me that. I don't need this. I don't need this. I plug my numbers in. My sample size was n equals 12. It was 12 people. Degrees of freedom was 11. So my t statistic was 3.54. My p-value was 0.0023. And again, if I've named the test, that's all I need on my paper. So you don't need this. You don't need this. When I'm teaching it to my students all year, you know, I have maybe stricter rules all year. But as we get closer to the AP exam, you know, we want you to maximize 1 year time and 2 year score. So if you name the test, you don't need this here. So again, if you've seen any of my sessions, this is probably going to feel somewhat generic-y, but since our p-value of 0.0023 is less than our assumed significance level alpha is 0.05, we reject the null hypothesis in favor of the alternative. So that I pretty much say for all hypothesis testing. That sentence is sort of the same. I've got my p-value in there. I've got my assumed significance level. I've compared them. I've linked them. And I've made a decision. I'm rejecting the null hypothesis in favor of the alternative. What I don't have is any context, so I need that second sentence. The data provides convincing evidence that on average, people who completed the program have increased their manual dexterity or something like that. So I'm sure Luke's talked about it as well. Those are kind of the 4 steps we need. And that's a full-blown inference-free response. And that, you know, that could take a little bit of time to do. So hope that helps. I'm going to come up with a 2-sample hypothesis test. And this is going to be even more work. So this is probably going to finish up the rest of the afternoon here. So hopefully you can read that okay, and let me just give you a minute or so to read that, and then we'll dive right in and we'll probably finish up today's session with that. So this is from the 2002 exam. This was free response question number 4. Okay, baby walkers are seats hanging from frames that allow babies to sit upright with their legs dangling and feet touching the floor. I vaguely remember having one of those as a kid, and I remember it being kind of fun. Walkers have wheels on their legs that allow the infant to propel the walker around the house long before he or she can walk or even crawl. So I think the little kids think it's fun, right? They can move around. They can't walk yet or crawl, but they can get around in their little thing, their little walker. Typically, babies use walkers between the age of 4 months and 11 months. Setting the stage, just giving you a little bit of background on the problem. Because most walkers have tray tables in front that block babies' view of their feet, child psychologists have begun to question whether walkers affect infants' cognitive development. So they can't see their feet. Is that somehow impacting how their brain develops? I'm a math teacher, no idea. But I can analyze the numbers probably, right? So that's what we want to do. One study compared mental skills of a random sample, I like that word, that's a good word, I'm going to underline that, of those who use walkers with a random sample of those who never used walkers. So I'm trying to compare 2 groups. A group of babies who had used walkers and a group of young children that didn't. Mental skills scores average 113 for 54 babies who use walkers, standard deviation of 12. So that's probably important. I'm going to write that down somewhere on my paper. And 123 for babies who did not use walkers, standard deviation of 15. So one group had mental skill score of 113. The other group had 123. I don't know exactly what those numbers mean, but we don't need that for the problem. Sample size of 54 for the first group and sample size of 55. That's good. I'm pretty happy. These are decent sample sizes. They were randomly selected, so I'm feeling pretty good about both of those. This one had a standard deviation of 12, and this one had a standard deviation of 15. So this one had a little smaller standard deviation. Again, I can't look at those numbers any faster than you can and make some decision here. Is there a difference between the two groups? I honestly don't know right now. So I'm gonna have to probably run a test here. Part A, is there evidence that the mean mental skill score of babies who use walkers is different from the mean mental skill of babies who do not use walkers? Explain your answer. So again, here's my 4 questions. Does this feel like a confidence interval or hypothesis testing? I think I'm gonna lean with hypothesis testing here. Do I have 1 or 2 samples? Well, I clearly have my 2 samples. Are we dealing with means or proportions? Well, 113 and 123 feels like means, and at some point am I going to look at a t-table or a z-table, and with means I'm typically looking t. So I think the first thing I want to do is name that test, a 2-sample hypothesis test with means. Gets me in the problem, going to help me perhaps find it when I go to the calculator. So that's the first thing I want to do. Always in those 4 questions, hopefully get my kids kind of in the game and looking at the correct problem. So of course, first thing I want to do is my null and alternative, right? So I said my null hypothesis, mu of W, the population mean of those with walkers, is equal to mu of NW, non-walkers. And my alternative was mu of W, walkers, was not equal to mu of NW, non-walkers. And I got that right up here, is different. So there was no direction there. So it's a 2-tailed test or 2-sided test. Always, always, always identify your parameters. So I said mu of W is the population mean mental skill for babies who use walkers. Mu of NW is the population mean mental skill for babies who never use walkers, or something like that. There's lots of ways to do that. But super important that we have the correct null and alternative, and we've identified my parameter. These are the numbers that they gave me. So the sample mean for walkers was 113. There were 54 children in that group, and the standard deviation was 12. X bar of NW non-walkers was 123. There were 55. Standard deviation of 15. Those are pretty good numbers. I like those. Those seem to be large enough. Always would want more, but I'm pretty happy with those 2 numbers. We'll come back to part B here. I really like this problem because of part B, but for now, let's just sort of continue on with hypothesis testing. Okay, so the first thing I need to think about is my degrees of freedom. Okay, so with degrees of freedom here, sorry, I'm on the wrong page. Let's do our conditions. Both samples were randomly selected as stated in the stem of the problem. Okay, that's good. We don't want just, random and check. That's not checking the conditions, that's putting a check mark. So just say that in words, and that's pretty important here. Both sample sizes are greater than 30, 54 greater than 30, 55 greater than 30. That's good. I'm feeling pretty comfortable about that. Population greater than 10N. Again, this was an older problem, and this was not part of the rubrics, but it is now, so I wanted to get that in. Is the population for the walkers greater than 10 times 54, 540? Yeah, it feels like that's a reasonable assumption. Is the population greater than 10 times 55 or 550 for the non-walkers? Again, probably follow that up with some words over here. Is reasonable to assume that the 2 populations are greater than 540 and 550. So I think we're good here. I've correctly named the test, I hope. I do not need that formula right there. And that's not an easy formula perhaps to come up with. That is not provided on the formula sheet. So we can avoid that if we want. And I stress to my kids as we're getting closer to the AP exam to not worry about that. Go to your calculator, get these numbers. If you've named the test correctly, you do not need this. Plug the numbers in. Again, I don't need that. I've got my critical information here, so let's go to the calculator and see if we can get those numbers. So we got to figure out what test to use. I think I called this a two-sample hypothesis test with means or something. Well, that's not exactly what the calculator calls it, but I think I could find this pretty quickly, right? I don't like two-samp t-test. I don't allow my kids to do that. That feels like calculator speak to me, and that's not good statistical communication. So I've called it something different. We have data here, and so my X bar 1 was 113. Standard deviation, again, this was just given to me. I'm just looking back on my paper here. Sample size of 54. My mean for non-walkers was 123. My standard deviation was 15. My sample size was 55. My alternative was not equal. And so if the calculator asks you to pool, we'll say no. Let me give me a minute or two, and I'll come back to that. If the calculator says pool, say no. And I'm going to run my test. And so I think these are the critical numbers here. My t-statistic is negative 3.846. Now my p-value, and we do see this on the AP exam, is not 2.077, right? Probability is always between 0 and 1. So that's scientific notation here. So I just need to just be careful. We do see sometimes 2.077 in students, I just think, have forgotten this or haven't seen it. So my degrees of freedom, this is a weird number here, but I'm going to write that down on my paper. And I'm going to go back and finish up that problem. Okay, so I wrote down the t-statistic, my degrees of freedom, and my p-value. The p-value is really pretty small, so I think I know what I'm going to do here. But where the heck did this number come from? 102.83. That's a weird number for degrees of freedom. So years ago, before we had calculators, we had to kind of make some assumptions that perhaps weren't great, but it was the best we could do. So we have options with degrees of freedom, and I'll tell you, personal opinion, what I like the best. We could take the smaller of my two samples. So the number of walkers minus 1 is 54 minus 1, or 53. Or the numbers in the non-walkers is 55 minus 1, or 54. So I could use that smaller of degrees of freedom and go to a t-table, go to my calculator and get that number. That's pretty conservative, and that's not very realistic in the real world. And with technology, I'm not sure I would do that, but that's an option. Pooled is basically adding the two sample sizes and subtracting 2, or n minus 1 plus n minus 1. So I got 54 plus 55 minus 2 is 107. Again, we did both of these years ago when we didn't have technology and we were trying to make our lives easier. Neither one is perhaps the best way to do it today or the most accurate. To pool here, I think we need to assume that the two population variances are the same, and that's a huge leap. That's something that I can't get from this problem and from that data. So I tend not to like either one of those two. The calculator is using what we call a Sader-Whorf formula. You don't need the name of that. One of my slides had that really ugly formula. I glossed over that. But that's where that number is coming from. I just wanted you to know that that's not magic. It's coming from a formula that's not in the scope of the course. You may never have seen it. Your teachers may never have brought it up, and that's perfectly fine. But if you've said to yourself, where does that number come from? It's coming from what we call I think I'm saying it correctly, the Sader-Whorf formula. Okay. What I do know is we had a really small p-value, right? 0.0002 when I took that scientific notation and made it a decimal. So I need to make some conclusion here. Again, first sentence is going to be pretty generic, pretty general. Since our p-value of 0.0002 is smaller than our assumed alpha level, assumed significance level alpha 0.05, we reject the null hypothesis in favor of the alternative hypothesis. That's a good first sentence, but it has no context. It's not related to our problem at all. So here's my conclusion in context. The data provides convincing evidence that the mean mental score of babies who use walkers is different than the mean mental skill of babies who did not use walkers. And that's really what we were trying to figure out at the beginning of the problem. Okay, so hopefully that's feeling better, and maybe I've demystified a little bit with this whole degree of freedom. Again, we're not sure exactly where you were in the course with your teachers and how much they taught you. Sort of, I guess, 3 different options, and I always like going to the calculator. It's the most accurate, and it's the best we can do. What I didn't do, and I really wanted to, and I think it's going to end up maybe time this better today, is part B of this problem. So part B says, suppose that a study using this design found a statistically significant result. Well, it sort of feels like we did, right? We had a really small p-value. Would it be reasonable to include that using a Walker causes, boy, I'm going to underline, circle that word. That's a strong word in statistics, right? Would it be reasonable to conclude that using a Walker causes a change in mean mental skill? Explain your answers. When I give this problem in practice with my kids, I use this every year. Unfortunately, almost all of them will say, yes, we can make that assumption, and it does cause. When I hear the word cause, I think causation, I think experiment. And this is not an experiment. This was an observational study. We had 54 babies in one group and 55. It doesn't feel like this was an experiment, and so I don't think I can talk about causation here. I think that low p-value sometimes leads students into, oh, we've proved it. There's definitely causation. It's so low. We have strong evidence, but we can't talk about causation here at all. So it would not be reasonable to conclude that using a Walker causes a change in mean mental skill, because this was an observational study, and a causal relationship cannot be inferred. So we just can't do it. It doesn't matter how big or how small that p-value is. We just can't talk about causation unless it's an experiment. So I'm getting close to that magic hour. Let me just wind down real quick. Okay, so we did that problem. We did that. This was another matched pairs that I unfortunately just didn't have enough time to get to. But if you want to take a look at another matched pairs, it's 2000 free response number 4. That's the problem that we just did. So hopefully by now you're feeling more comfortable with both confidence intervals and hypothesis tests with means, both 1 and 2 samples. Okay, that's what Luke and I did the last couple of days, right? In proportions on Monday and Tuesday. Similar to other inference test procedures, you should be able to write a clear, concise solution in context. It's so important. Readers will be saying, is there any context? Is there context? We want you to relate it to our problem. The term we use is the student in our problem. You can see I have some generic interpretations. Those are great, but I always want to make it specific to our problem. And that's the context. Here's the homework for tonight. Luke tomorrow is going to do type 1, type 2. Super important. And power, that's a little trickier concept. So Luke will do a great job with that. But tomorrow Luke will do type 1, type 2 power. So here's your homework problem. He posted on his website. So for the sake of time, I'll let you guys go ahead and do that. And again, this was modified. There's a part A to the problem, but part B says, in the context of this situation, describe a type 1 and type 2 errors, and describe the consequences of each of these for the law firm. So I've graded some type 1, type 2 problems. Students tend to be pretty good about telling the difference. What is a type 1 versus type 2? Sometimes, though, the consequences of making a decision or making an error in this case, they struggle with. So make sure you talk about type 1 and type 2, but what's the consequence, or what are the ramifications of making the wrong decision here? Okay, so this is typically one of my last slides here, but we know that all students do not have access to the internet or a device. I'm struggling that with my students. I have 4 different classes this year at John Baptist, and some of our students are struggling with internet connectivity, or they don't have a device, and it's a real issue, and we're going to try and help you solve that. So the College Board is working on solutions to help students get what they need to show their best work. If you need mobile tools or you have issues with connectivity or know someone who does, please reach out to the College Board. They'll bend over backwards to help you guys. We want you to take this year's modified AP Stats exam. Luke and I want you to do a great job. We want you to take more statistics in college. And so if that's a problem, please let somebody know, and we'll try and help you out. So again, thanks for watching today. It's getting worse out as I'm looking out my window. It's rain now. It's going to turn into some snow, and hopefully you couldn't hear the wind and I didn't lose power, and I was a little worried about that. But anyway, have a great afternoon. I hope everyone's safe and healthy. Let's stay positive. We can beat this thing. Keep working hard. And on the website there, I gave you that link to, you can look at the schedule for the rest of, I guess, our 3.5 weeks with Luke and I, and can plan your review accordingly. So be safe. Enjoy your afternoon, and I'll see you next week. Thanks a lot.